There's a $2 mineral sitting in the masonry section of every hardware store in the country that stops iron and steel pipe corrosion permanently at the molecular level. Not slows it, not delays it. Permanently converts the iron oxide forming on metal surfaces into a chemically stable glass-like barrier that water, oxygen, and salt can no longer penetrate. The United States alone experiences approximately 260,000 water main breaks every year, costing over $2.6 billion in emergency repairs. The American Society of Civil Engineers estimates that drinking water infrastructure alone needs $105 billion in pipeline rehabilitation over the next 2 decades. The global pipe market was valued at $137 billion in 2024, and a compound that has been used to protect metal surfaces since 1818 sits on hardware store shelves at $2 a quart, doing the job that billion-dollar pipe replacement programs are being built to address. The mineral is sodium silicate, also known as water glass. Its chemistry has been documented for over 2 centuries. Its effectiveness against iron and steel corrosion confirmed across 32 consecutive years of field trials on East Coast water systems. Welcome to the Buried Manual. This is where we open the vaults the industry welded shut. Now let me take you back to where this all starts. The year is 1818, and a German chemist named Johann Nepomuk von Fuchs is working in a Munich laboratory on a problem that has resisted solution for centuries. He wants to create a material that bonds permanently to stone, metal, and masonry surfaces and hardens into something chemically stable, waterproof, and impervious to atmospheric changes. The compound he synthesizes by treating silicic acid with an alkali is sodium silicate, a water-soluble compound that dries into a rigid, transparent, glass-like film wherever it is applied. Von Fuchs immediately recognizes the range of what he has created. It can preserve stone and masonry from weathering. It can create fire-resistant coatings on wood and fabric. It can seal porous surfaces against moisture penetration. And when applied to iron or steel, it forms a microscopic barrier between the metal surface and the corrosive environment that normally destroys it. For the next century, sodium silicate would be applied across dozens of industrial and construction applications, slowly accumulating a documented record of performance that the plumbing and pipe replacement industry would eventually need to work very hard to keep out of mainstream consumer awareness. The ancient Romans, who built some of the most durable infrastructure in human history, had no sodium silicate, but they understood the principle instinctively. Roman engineers applying volcanic pozzolan mortars to aqueduct and cistern walls were creating silicate-based barriers between the masonry and water that explains why structures built 2,000 years ago still hold water today. The silica-calcium chemistry of Roman mortar formed a film on exposed surfaces that functioned as a natural corrosion inhibitor, the same fundamental chemistry that von Fuchs would later isolate and concentrate into a commercial compound. The Romans documented that certain volcanic ash treatments applied to iron fittings and water infrastructure extended the useful life of those fittings dramatically beyond what was observed in untreated components. They did not have the chemistry to explain why. Von Fuchs, 18 centuries later, provided the explanation. And by the mid-20th century, field engineers applying that explanation to real infrastructure had 30 years of data demonstrating exactly how significant the results were. Here is the chemistry that separates sodium silicate from every other pipe protection compound sold at retail. When iron or steel begins to corrode, the surface of the metal reacts with oxygen and moisture to form iron oxide, the orange flaking compound we call rust. Iron oxide is structurally weak, porous, and electrically conductive, which means it accelerates rather than protects against further corrosion. Every rust spot on a pipe becomes a corrosion engine that actively destroys the surrounding metal faster than the original surface would have degraded. Sodium silicate applied to iron or steel surfaces reacts differently. The silicate ions in solution bond with iron ions at the metal surface, forming iron silicate compounds at the interface between the metal and the environment. As the solution dries, it polymerizes into a continuous glassy film across the treated surface. This film is hydrophobic, chemically inert, and physically impermeable to the oxygen and water molecules that drive the corrosion reaction. The corrosion does not slow down. It stops because the reactants that drive it cannot reach the metal. In 1960, a paper published in the journal Corrosion documented something that should have permanently changed how the pipe protection industry approaches metal infrastructure. Researchers had been tracking sodium silicate treatment of galvanized iron, galvanized steel, yellow brass, and copper water piping in thousands of buildings across East Coast cities for 32 consecutive years. The results were unambiguous. Properly controlled sodium silicate treatment eliminated rusty water completely, maintained satisfactory flow rates through treated piping systems, and minimized pipe failures due to pitting and clogging by corrosion products. Comparative field experiments confirmed the protection mechanism. The study authors documented that most cases of poor results from sodium silicate treatment resulted not from any deficiency in the compound's chemistry, but from improper application methods, poor plumbing design, or inadequate system control. The compound itself worked. It had been working consistently for 3 decades across thousands of building installations. The document went into the technical literature and stayed there, largely invisible to the homeowners and building managers who needed it most. By the 1960s and 1970s, the PVC pipe manufacturing industry was building the commercial infrastructure that would eventually render this documented chemistry almost irrelevant to the mainstream market. Polyvinyl chloride pipe does not corrode at all. A pipe that cannot rust does not need a rust inhibitor. But the millions of miles of galvanized steel, cast iron, and copper pipes installed in American buildings during the construction boom of the 1940s and 1950s were not going to be replaced overnight. They were going to rust, leak, and eventually fail, generating repair calls, pipe replacement contracts, and the service revenue that the plumbing industry depends on as its primary business model. A $2 treatment that extends the service life of galvanized steel pipe by decades does not generate service revenue. It prevents it. And the prevention of service revenue is not something any service industry documents in its consumer-facing communications. The economic scale of pipe corrosion and failure in the United States is enormous by any measure. The NACE International Corrosion Cost Study, the most comprehensive analysis of corrosion's economic impact ever conducted in the United States, estimated total direct corrosion costs across the American economy at $276 billion annually, representing 3.1% of GDP at the time of the study. The water and wastewater infrastructure segment alone contributes billions to that figure annually through pipe failures, emergency repairs, and scheduled replacement programs. The U.S. plumbing industry was valued at $169.8 billion in 2025. North American utilities experience approximately 260,000 water main breaks every year. These numbers represent the commercial ecosystem that depends on metal pipe infrastructure degrading at its natural rate. Sodium silicate and other silicate corrosion inhibitors represent a documented mechanism for dramatically extending the service life of existing metal infrastructure, reducing the failure rate, and consequently reducing the service and replacement revenue that the industry generates from pipe failure. The U.S. Environmental Protection Agency and the National Sanitation Foundation both recognize sodium silicate as an approved corrosion control agent for specific applications in water treatment systems. The EPA's National Primary Drinking Water Regulations specifically reference silicate inhibitors as potentially effective in controlling corrosion of lead and copper in water distribution systems. NSF ANSI Standard 60 establishes a maximum allowable level for sodium silicates as corrosion control agents in water treatment contexts. PQ Corporation, one of the world's largest sodium silicate manufacturers, publishes technical documentation confirming that sodium silicate solutions form a thin protective film on iron, steel, copper, and galvanized pipe surfaces that prevents corrosion progression when properly applied. This is not fringe chemistry. It is documented industrial chemistry, regulated by federal environmental agencies, and confirmed across decades of field application, while hardware store shelves stock the same compound at $2 a quart. The suppression is architectural rather than deliberate. Plumbers are trained in pipe replacement, pipe joining, and pipe installation. They are not trained in corrosion chemistry or surface treatment science. The training programs, trade publications, and continuing education courses that form the professional knowledge base of the plumbing industry are funded and produced by fixture manufacturers, pipe manufacturers, and product distributors, whose revenue depends on installation and replacement, not on prevention. A homeowner who treats their aging, galvanized pipes with a sodium silicate solution and extends the useful life of that pipe system by 15 years is a homeowner who does not generate a pipe replacement contract. The structural incentive of the service industry points entirely away from prevention and entirely toward replacement, and the consumer knowledge base reflects that incentive perfectly. But here is what that architecture cannot change. Sodium silicate has been documented as a metal corrosion inhibitor since 1818. Its mechanism of forming a glassy protective film on iron surfaces has been confirmed by 2 centuries of industrial application. Its use in protecting metal water infrastructure from internal corrosion was confirmed in 32 years of continuous field trial documentation published in peer-reviewed engineering literature. It is manufactured at industrial scale for dozens of applications, sold as a commercial product at costs between $2 and $5 per quart, and available without restriction at masonry supply stores, hardware retailers, and concrete sealant suppliers under names including sodium silicate solution, water glass, concrete densifier, and liquid glass. The chemistry is not proprietary, the compound cannot be patented, and the protection it provides to aging galvanized steel and iron pipe surfaces has never been scientifically disproven. The applications for sodium silicate as a pipe and metal corrosion protection tool are specific and important to understand precisely. Sodium silicate applied externally to the outside surfaces of metal pipes, structural steel, iron gate hardware, garden tool surfaces, and outdoor metal fixtures provides the same corrosion protection mechanism that makes it effective in industrial applications. The compound is applied in thin coats to clean, dry metal surfaces and allowed to cure into the glassy protective film. For outdoor metal structures including fence posts, gate hardware, metal garden furniture frames, structural beams, and pipe fittings exposed to weather, sodium silicate provides a documented protective barrier against moisture-driven oxidation. It is the same compound used in concrete floor densification, in fire-resistant coatings, in industrial foundry mold making, and in dozens of other applications where a permanent, chemically stable mineral barrier is required on a surface. The application method for external metal protection with sodium silicate is simple. Begin by cleaning the metal surface thoroughly to remove any existing rust, dirt, oil, or grease. Wire brushing existing rust to the extent possible improves adhesion, though sodium silicate can penetrate and stabilize light surface rust in a manner similar to its behavior in concrete pours. Allow the surface to dry completely. Apply sodium silicate solution in a thin, even coat using a brush, roller, or foam applicator pad, working it into any crevices, joints, or pitting on the metal surface. The solution will appear milky or slightly cloudy during application and will clear as it dries. Allow the first coat to cure for 24 hours. Apply a second coat following the same process. 2 coats produces a durable, continuous glassy film across the treated metal surface. The cured film is hard, smooth, resistant to water penetration, and stable across the temperature range experienced by outdoor metal structures in any climate. The historical record of sodium silicate's use in protecting iron and steel infrastructure stretches from Roman volcanic mortars to 19th century European industrial applications to 20th century American water system field trials. What changed between the documented effectiveness in those 32 years of East Coast building trials and the present day is not the chemistry. The chemistry has not changed. What changed is the commercial structure of the pipe and plumbing industry. Pipe replacement generates recurring revenue. Pipe protection generates a one-time material sale. Every year that a sodium silicate-treated pipe system does not fail is a year that does not generate a plumber service call, a pipe replacement quote, or a building infrastructure upgrade contract. The compound sits on hardware store shelves at $2 a quart. Its 2-century record of performance visible to anyone who reads the engineering literature, invisible to anyone whose knowledge of pipe protection comes from the plumbing industry's consumer-facing communications. The American Society of Civil Engineers gives American drinking water infrastructure a D grade in its infrastructure report card, reflecting a system that loses an estimated 6 billion gallons of treated water every day through leaking pipes. The United States needs an estimated $452 billion to replace aging water mains, with 20% of installed pipe systems already beyond their useful lives. Every failed pipe in that system represents a corrosion process that was theoretically preventable. Every emergency repair generating thousands of dollars in plumbing service revenue represents a failure mode that a $2 silicate solution applied at installation could have delayed by decades. The compound that von Fuchs synthesized in 1818, that field engineers documented in 32 years of continuous trials in the 1960s, that the EPA and NSF have recognized as a legitimate corrosion control agent, sits on the shelf and waits for someone to remember that it was always there. Corrosion does not care about service revenue. Iron oxidizes in the presence of oxygen and water whether or not a plumber gets paid to fix it. The silicate film that stops that oxidation has been available since the early 19th century, documented in field trials since the mid-20th century, and priced out of consumer awareness since the moment the pipe replacement industry built a business model around the alternative. A $2 quart of sodium silicate applied to the external metal surfaces of aging galvanized pipes, gate hardware, outdoor structural steel, and iron fixtures provides a documented corrosion barrier that costs less than the call-out fee for a single plumbing service visit. The chemistry works, the documentation exists, and the hardware store shelf where the compound sits has been waiting 200 years for you to read the label. Subscribe and share this video. Every share puts this knowledge in the hands of someone still paying hundreds of dollars to repair what $2 could have prevented. The next vault opens soon.